Hello, today we discuss black box testing. Black box testing does not make use of program text, so the program is a black box for us. We don't see inside it. Black box testing can be both functional or non-functional. Today we discuss functional black box testing. There can be several methods to use specifications for testing, and today we're going to discuss two of them: equivalence partitioning and boundary value coverage. So the tests are derived based upon the task or specification, and the outputs are estimated also based on the task specification. This is in contrast with the white box testing, where the inputs are derived or designed based on the program. Equivalence partitioning involves partitioning the input domain into a collection of subsets which behave similarly from the testing point of view. And this similar behavior means that if one test from this subset fails, then all other tests also fail, and vice versa. If a test is successful, doesn't fail, then all the other tests would be successful as well. So we need just to test one test from each equivalence class. So this is one optimization. It enables to replace perhaps billions of values for example, some kinds of inputs, to replace these billions of values with just one input from each class. The other optimization is that if we have several inputs, then we will not test all the combinations. We test perhaps all values. This can be done in different ways, but testing all values, not all combinations, can be optimization number 2. Well, here is a picture of an input area. So here is one equivalence class, and we assume that if one test from this area is correct, then all the other tests are correct as well, and if one test fails, then all the other tests fail as well. Of course, this doesn't mean that all the tests in this, or all inputs in this area, give the same results. This is a different thing. Equivalence classes can be found on different ways. For example, we could, if it's an ordered interval of numbers, then I could take one test inside this ordered interval and two tests outside it. If it's bounded only from one side, we could take one test inside and one test outside. If this is a set which has similar values, for example, a set of values that are processed similarly, and another set of values which is processed similarly, then we can take one value from both sets. If it's a condition yes, no, we could take both yes and no. For the boundary values, we could take values on the boundary and a little bit less, a little bit more than the boundary, and a very small value and a very large value for real numbers. For integers, we could take the boundary, one less, one more, large negative, large positive. For an ordered set of values, I might take the border and the preceding, the following, and the starting and maximum or finishing value of this ordered set. How do we use these equivalence classes and boundary values that we identified? So the process of designing a black box test set. First, we need to distinguish the input and output data equivalence classes, sometimes also input-output combinations. We need to select data in each equivalence class and in boundary values, and this was the optimization 1. If we have a real number from 0 to 10, then a possible number of inputs from this range is very, very large, but we will take only one of these. Then we combine those data into tests. If we have two inputs, we can combine as many correct equivalence classes as possible into one test, because the correct data can be combined between each other. And we can have errors usually just by one, because very often if we have different inputs, then an error in one input will already stop processing, and we don't see the effect of this of the error in the other input. So errors are collected in the tests just by one. Then we evaluate corresponding outputs based on the specification again, identify tests, compose a testing plan, test, and estimate. So this is the process of black box testing with equivalence classes and boundary values. Here is an example. We have two inputs here. These are volume and unit price. And the output is batch total price. The volume, depending on the volume, there are different discounts. So for volume from 1 to 4, discount is 0. From 5 to 9, discount is 8%. For volume from 10 to 25, discount is 15%. We consider no errors, so consider only values inside these boundaries given. Now, what are the equivalence classes and boundary values in this case? For the unit prices on the y-axis here, we have the equivalence class between 10 and 1000. So somewhere here we should take our value. We have boundary values 1000, 999, 11, and 10. If we would consider errors, then we would have also boundaries more than 1000, less than 10. Perhaps we should distinguish negative values because they may be processed in a different ways. But for this case, when I do not consider errors, we have just 5 equivalence classes. For the volume, our equivalence classes are inside this first class from 1 to 4, inside the second class from 5 to 9, and inside this third class from 10 to 25. Again, if we would consider errors, we might have also volumes 0 or less, or volumes larger than 25, but we do not do this at this moment. For the boundaries, we have the boundaries 1, 4, 5, 9, 10, and 25. So altogether we have 5 boundaries and the boundary values and equivalence classes for the unit price, and 1, 2, 3, 6, 9 equivalence classes and boundary values for the volume. Now, if we would combine all these boundary values and equivalence classes for these two inputs, we would get 5 multiplied by 9, or 45 different tests. This is clearly quite a lot. It may make sense to combine them in this way, but usually it is sufficient to just have all the equivalence classes and boundary values tested without testing all the combinations. And it's given in this picture. So we have tested, let's look at the volume equivalence classes. This boundary, this class, boundaries, classes. These are all tested. Similarly, we have included in the tests all, well, there is one equivalence class from 10 to 1000 and 4 boundary values for the unit price. So for 1000, 999, this is intermediate, then it's 11 and 10. Well, some values may be repeated. We see that all combinations are not covered, but all boundary values and all equivalence classes from both inputs are covered. And now we have only 1, 2, 3, only 9 tests that cover all our equivalence classes and boundary values for all inputs. So this is the second optimization. There are many other methods that can be used for white box testing. They are considered in the lecture, or you can find them in the materials. But for this video, the outcomes are, so the notion of black box testing, and why this name, of course, idea of equivalence partitioning, idea of boundary value coverage. We make 2 optimizations. What kind of optimizations are they? And in the materials, there are a lot of materials about black box testing. Please find other methods for testing programs without knowing their internal structure, or black box testing. And as always, we have the Moodle course, Software Quality, tarkvaras kvaliteet, and alternate download on teppandi.ee. See you, and thanks for listening.